So today we're going to talk about combinations, but before we talk about combinations, I want to talk again about permutations just so you can see how they are related to one another. So at the last lecture, we started talking about counting things, and to start counting things, we started giving the example if I wanted to order A, B, and C and how many different ways I can do that. So we started by doing a number tree basically, so we could see all the, and then from each of those branches we only had two options to choose from. And the last one we only had a single option left that we were able to choose from. So that meant that we had three options, then two options, then one option. So to figure out how many total options we had, we could just multiply these numbers together. So I could have multiplied 3 times 2 times 1. So that would have been a pain to constantly be able to do. So we started talking about how permutations allows us to take this number tree, and instead of saying 3 times 2 times 1, this is really just 3 factorial. So for our permutations, it was always going to be the number of objects factorial to give us the total amount of different possibilities we have. So then going off of that, we then said, hey, we want to be able to choose or pick a couple of the numbers. So instead, if I had A, B, C, D, E, and I said, hey, I want to see how many different ways I can rearrange these, but only picking 3 of the letters. So that means I was only having space for 3 of them. And we saw that we had the formula for NPR, which was equal to N factorial, so the amount of objects factorial, over N minus R factorial, where N was the total number of objects, so I had 5 objects here, and R was how many options I wanted, and I wanted 3. So in this case, this would have been 5P3, and we could have done that and figured out how many different options we had. So this all matters if the order that these letters were in actually mattered. So if A comes before B, which comes before C, if that order matters, then this is how many different options we would want. It matters that we have these 3 objects, and those are the 3. So for today, we're going to be talking about those combinations. So our combinations is going to be a lot of similarity between this. It's actually NCR. So a lot of people say N choose R. That verbatim is used a lot. You may also see it written like this, and we are actually going to use this notation a lot. So we're going to be using this notation a lot in later lectures. But basically the equation for choosing 3 objects, like we can go back to this saying we had 5 objects and I only want to choose 3 of them, but the order that they appear in doesn't matter. This formula is going to be basically identical, except one piece is different. And that piece is right here. We're actually going to be dividing by R factorial. And what that is doing, it's basically saying, hey, I'm finding all the different permutations. So this right here, this R factorial, so I'm looking at all the different ways I can rearrange 3 items, and I want to divide that out because I only want it to happen once. So I don't care if it's A, B, or C. I don't care if it's A, C, or B, or B, C, A, or any of the 6. I just care that they contain those 3 letters in whatever order it may be in. So this is also a button in your calculator. So again, if you need help finding that button, just send me a message and I can help you find it with your particular calculator. But we're going to be talking about N choose R. So this is when order does not matter. So it doesn't matter which way these objects are rearranged. It just matters that we have those 3 objects. On the other hand over here, this was giving us all of those combinations when the order actually mattered. So it would be A, B, and C, that would count for one, A, C, B, that would count as another, so forth and so on. So over here, this piece right here is taking all of those different combinations of those three and dividing them out. Alright, so we're going to do a couple examples. So a lot of the times the examples are, you need to figure out which of the two you're talking about. Are you talking about permutations where the order mattered, or are you talking about combinations where the order does not matter? So let's look at a couple of the examples from the slides and figure out first which of the two we're talking about. And then we're simply just going to be putting it into our calculator, either you using the formula or you using this button. I highly recommend you find this button because it will make your life really easy. For those of you that may not have a calculator, I will search online for one of these calculators that have these buttons for you online, that way, and are posted on my website for you, so you can use that later on. So let's go look at an example. Alright, so first example, it says a president, a vice president, and a secretary are chosen from a 25-member garden club. All right, so we want to try to figure out how many different ways we could have a president, a vice president, and a secretary given 25 members. So the fact that one has to be the president, one has to be the vice president, and one has to be the secretary, that's showing you that the order matters here. So we actually have an order that matters, so this problem is going to be a permutation problem. So we have 25 objects. So we said order matters, so this is going to be a permutation. And there's only 3 spots we care about. So our R value is going to be 3. So you could plug this into your calculator, you could put it into an equation, whatever, but this gives us 13,800 different ways that from 25 people we can come up with a president, a vice president, and a secretary. That's a lot of different ways we can rearrange 25 people. Alright, so the next one. So this was the first one on the slide for the examples. The next one says a cook chooses 5 potatoes from a bag of 12 potatoes to make a potato salad. So looking at this one, we're just picking 5 potatoes. It doesn't matter how those 5 potatoes are put into this pot or done with whatever. We're just picking 5 random potatoes and putting them in the pot. So here the order does not matter because I'm just picking 5 potatoes. Doesn't matter how I pick them. It's the same 5 potatoes no matter which order I'm looking at to make this salad. So this one is going to be a combination. So we had 12 total objects, so 12 potatoes, and we are trying to choose 5 of them. So 12 choose 5. So doing that, we have 792 different ways we can make this potato salad. So the next one is a teacher is making a seating chart for 22 students in a classroom with 30 desks. So we have 22 students. We're trying to place them in 30 desks. We have to decide, does the order matter? Does it matter where Vivian is going to be sitting or where, I don't know, Sally needs to sit? So it does. As a teacher, I need to know where every person is, so the order does matter, especially to me when I'm taking attendance. So on this one, the order matters how I'm putting you in these 30 desks. So I could rearrange you in tons of different ways. So let's figure out how many different ways I can arrange 22 students when I have 30 desks. And this is actually pretty close to our classroom for some of you. So I have 30 different objects total that I am able to place somebody in. Since the order matters, this is going to be a permutation, and I'm trying to choose 22 of those desks because I'm trying to place you in 22 of those desks where the order matters. So doing this computation, I get a really big number, huge. So 6.58 times 10 to the 27th power. That's how many different ways that I could make a seating chart if I had 30 empty desks and trying to rearrange it with 22 students. This is a huge number. That's basically, if I added 25 more zeros after that 8. That's huge. Different ways I can just rearrange you by just placing you in different places. So that's why my job is so hard. Alright. So let's look at a couple more examples. So one thing you need to understand about choosing objects is that there are two special cases. So if I have, doesn't matter how many objects, if I'm choosing none of them, so that means how many different ways can I choose no objects? And that answer is always 1. There's only one way to choose nothing. Same goes with the other way. So if I have some amount of objects and I'm trying to choose all of those objects, there's only one way I can choose every single object. So these two things are going to be very special. Also, know for your R can never be greater than N, because this would just equal 0. There's no way for you to be able to choose some amount of objects if you don't have all of those objects. So if your R value is ever greater than N, it just means you can't do it. You can't choose more than you have. But here, if you're trying to choose 0, the outcome's always 1. This is called the empty set. And if you're trying to choose all of them, you also get 1. So these are two special ones that we are going to talk about. So empty set, entire set. We'll get to that in a little bit. Alright. So let's say the Georgia Lotto requires winners to pick 6 integers between 1 and 46. The order in which you select them does not matter. So it doesn't matter if you had selected 38 before you selected 24. You just care that you got all of those numbers correct. So the order on this one does not matter. And we want to figure out how many different lottery tickets are actually possible. So we're trying to choose 6 numbers. And we have 46 we can choose from. So how many different ways can I choose 46 different numbers? Because all the numbers are going to be different. So it's not like I can pick 46 and 46 and 46 and 46. I have to pick different numbers. So of these 46 numbers, I can only choose 6 of them. So if I can only choose 6 of them, let's see. I get 9 million different ways that I can choose 6 numbers from 1 through 46. That is a lot of different ways I can choose 6 numbers. That's why you have a 1 in 9 million chance of picking those 6 numbers correctly. Not a great look. All right, so the next one is one that actually is used often, especially in commercials, where they say, hey, we have millions of different ways that you can choose or make your own pizza if you go to one of those make your own pizza places. So this pizzeria offers any combinations of up to 10 different toppings. So how many different pizzas can be ordered if you choose 3 of those 10 toppings? So I have 10 different items I can choose between, and I'm trying to choose just 3 of those 10. So how many different ways can I choose 3 of those 10 toppings? So we can plug that into our calculator, and I get 120. So just by only trying to pick 3 different toppings, I have 120 different options if they gave me 10 options, which is a lot of different ways to make a pizza so far. So the next question, based off this exact same pizzeria, it says if we can choose any number of toppings. So because we can choose any number of toppings, that means we have to go and see all the different choosing between that 0 and that 10. So I need to see all the different ways to do this. So let's look at this. So this problem is we are trying to choose any number of toppings. So the first one, let's say that I choose 0 toppings. So if I have 10 and I'm choosing 0 of those toppings, that means there's only one possible way to make this pizza, and it's just plain pizza. So next we have 10 and we're trying to choose one of them. So that means I get out 10 different ways. So there are 10 different ways to choose when you have 1. So then the next one, so I'm now trying to choose 2 of these different toppings. So that gives me 45 different ways. So as you can see, we're going to keep on continuing this pattern because I want to see all the options with every single possibility. That means when I choose none, if I choose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can keep going. So 10 choose 3 gives us some number, which was 120. 10 choose 4 gives us some number. 10 choose 5 gives us some number. 10 choose 6 gives us some number. 10 choose 7 gives us 120. 10 choose 8 gives us 45. 10 choose 9 gives us 10. And 10 choose 10 gives us 1. So these are all the different ways that I could get for these different topics. So to figure out how many total ways, I just have to add them all up. So I just add 1 plus 10 plus 45 plus 120, so forth and so on. Add up all of these values. And when I add up all of these values, I get 10, 24. So I have 1,024 ways that I could make, or choices. I could have 1 if I chose nothing. If I chose all 10, again I would have 1. So by adding up all of those different possibilities, that allows me to see how many different combinations I could have, no matter how many I choose. So this is given no constraint. I can choose all of them. So this right here would be a pain to do if I had asked you to, instead of just 10, let's say I said 55 or something like that. That is a huge number, and I don't want to work out going through all of this 55 different times. Hopefully you see a pattern, because we're talking about that next class. But there is an easier way to do this. So we have an actual formula for choosing subsets of insets. So inset being, we have some random number and we're trying to figure out all the different subsets. So meaning if I only wanted to choose 1, if I wanted to choose 0, so forth and so on. So that subset of some kind of set is simply going to be 2 to the n power. And why it's 2 to the n power, you can kind of think about it as a binary sense, where your options are either 0, it never happened, or 1, it was on the pizza. So it's either not on the pizza or on the pizza. So that means I have 2 different choices for every single topping. So on that last one, if I just had done 2 to the 10th power, that also gives me 1024. Much easier, because again, I'm trying to find all the different subsets given 10 different items. Okay, so another example of this. So how many different answer keys are possible for a 10-question true or false problem? So we want to figure out how many different answer keys we could make for just 10 true or false questions. Well, it's this exact same number right here. Because, again, it's either true or it's false. So I have 2 different options it could potentially be. So if I want to figure out all the different subsets, it's just going to be 2 to the 10th power. And that includes, all of them being true or all of them being false, because it's not an on or off situation this time. It's either true or false. So you could pick all your 0s to be false and all your 1s to be true, and you can think about it that way. Alright, so that is it for the combinations lecture. We will have a short quiz on Wednesday. I will release the quiz after the lecture on Wednesday. Just take it by the end of the day on Wednesday. Again, if you are observing Passover, please just let me know so we can reschedule that quiz at a later date. It's no big problem at all. So I'm going to look to see if you guys have any questions at this time. Otherwise, you're good. So, Michael, if you hit the math button, you should be able to scroll to a probability section. So, like if you hit right a couple times, you should see a PROB, and then it should be in that list somewhere. Alright, so if you guys have any questions when you're doing either of those 2 homeworks, let's also make those homeworks due also on Wednesday when you take the quiz. So I'll send out a message later about that, so don't worry. Let's see. So, Kennedy, the 2 is basically going to be constant because it's always going to be either you have it or you don't kind of situation when we're talking about these subsets. Amari, if you click on that, it should be somewhere in there. It should be really close to your factorial button. So if you know where your factorial button is, that's where the NCHOOSE R and NPR buttons are.